Sorry, my mic was off. Good morning or good afternoon, everyone on Zoom. Okay, so first order of business are your midterm projects, and so I think I got everybody's. So I am in the process of grading them, so I plan on finishing the grading for the midterm projects by end of this week. So by Friday at the latest, you should know your score. Although I do plan on hopefully finishing it by tomorrow. So hopefully by end of day tomorrow, you'll know. I'm maybe one third of the way done right now, so I'm trying to leave as many kind of comments as I can. Just because the final project is going to be very similar to the midterm project. And so I would like to see so some of you have done really well in the midterm project. Others I've left some feedback for you to help improve by the final project. So definitely make sure you're reading those as we kind of prepare for the final project. Okay. Speaking of final project, I will have the specifications for you by next Tuesday. So this week we have an ANSYS activity, and then next Tuesday we'll talk about the final project, and then we'll kind of move into kind of final production for this semester. Okay. Okay, but that's the plan. So from here on out, it's just kind of a steady diet of ANSYS activities on kind of more. I would say more niche features. We'll have plenty of time to work on. You'll have plenty of time to work on the projects in class, ask me questions, things like that. Okay, but to give you just a little bit of a preview of the final project is almost the same thing as the midterm project. Biggest difference is that you'll be able to choose your geometry, and so I know a few of you had asked me questions on the midterm project. If you can use something from work, or if you have some other ideas for the geometry. So final project is your chance to do an analysis on the geometry of your choosing. And the other big change is that you are going to have to. It is going to be a requirement for you to factor in one of these more advanced features within ANSYS. So activity 5, 6, 7, 8. At least two of those you're going to have to. I think it's either two. I think it's two. At least two of those activities you're going to have to factor into your final project as well. Okay. But besides that, it's very similar to the midterm project. So, same structure, same format things.
Can it be a 1 month thing?
Exactly. Yeah. So we're going to talk about the specifications on April, a week from today. So that's April 15th. And then you'll have until middle of May, basically. So the due date for the final project is going to be the Monday after finals week. So I think that's May 19th. So yeah. So a little bit over a month, just like the midterm. Okay, any questions, anything before we get started for today? Okay, all right, so let's go ahead and get started. Okay, so the topic for today, and kind of the topic for this week, activity 6, is this idea of optimization in finite element analysis. Okay, so for some of you in class, this will be a little bit deja vu because I did teach an entire course on optimization last semester, and some of you were in that course, and so you can think of today as kind of like a very, very, very fast kind of crash course in optimization. But of course, we're not going to be able to go through all the theory, all the different algorithms, all the different algorithms of optimization. Luckily for us, ANSYS actually has a lot of optimization tools built into it. So my goal for today is just to kind of introduce I would say the core concepts of what optimization actually is, what you need to set one up. And that's going to help set us up for on Thursday when we actually run an optimization within ANSYS itself. Right. Okay. So let's just start with the basics. So let's start by talking about what is optimization. Okay. So kind of in a nutshell, optimization is the process or kind of the goal of basically getting the most performance out of an engineering design as possible by tweaking the values of the various parameters that go into an engineering design. So that's kind of the best definition of optimization I can give in kind of a one sentence. I had to kind of double take for a second because I got a text from my wife. She said she got poisoned. But she was talking to, but she's playing Pokemon right now. So that's so the Pokemon was poisoned. She was not poisoned. I'm working right now. Just because she's awkward doesn't mean I'm not awkward. Okay, anyway. Okay, so whenever you have an engineering design, you know, there's lots of different parameters that go into, you know, that design itself, right? So for instance, you know, if we look at a, so if we look at a, you know, let's say like a building, right? So whenever you're designing kind of a solid part, you know, the first thing that comes to mind are the dimensions of the part itself, right? So we have the height, we have the width, and we have the depth. Okay. So that's three parameters here that basically define the geometry of our design. Okay. So depending on what we specify for those parameters, that's going to change our engineering design, right? And then, you know, let's say that, you know, you were trying to, you know, let's say for one factor for this building is you want to minimize the amount of air resistance or drag the building experiences in a windstorm, okay? And so in that situation, you know, that output or that, you know, aspect of our performance is going to be sensitive on our design parameters here, okay? And so if we were interested in minimizing the drag, or in other words, you know, minimizing maybe the energy cost of the building itself, we would think about kind of changing these three parameters. Okay. So we can tweak the values of these parameters, or we can kind of change their values, and that's going to change, you know, how our design is going to behave, how, you know, what the outputs of our, you know, analysis is going to be. Right? Another example, maybe one that's a bit more close to home, something that we've all done in this class, is let's look back at activity 3. So activity 3, we actually did a little bit of a design exercise in that activity, right? So if you recall from activity 3, that was our signpost activity. We had our signposts like this. And part of that activity, you know, I had you modify the diameter of the post here, so that the stress in the post was minimized, right? So, or we try to get it below the yield strength of the material. Okay. Okay, so that's another example of, you know, an aspect of our design or an aspect of our design's performance being sensitive to these parameters. Okay. And of course, you know, these are not the only examples. And so, you know, any engineering design that you have, you know, the result or the performance or, you know, the inefficiencies, things like that, they're going to be sensitive to these parameters. Okay. And so a big part of engineering design is, you know, how do we select these parameters in a way that maximize the performance, that minimize the loss, that, you know, maximizes the factor of safety, things like that. Right? No matter what engineering design that you were going to do, that's going to be part of the process at some point or Now, we haven't really been putting much thought into how we do this so far in this class, and so, basically, whenever there's a design aspect to an ANSYS activity, I tell you just to do trial and error, right? So, change the parameter, run the simulation, see how it changes things, and then go back and then do it and then do it again, okay? Turns out, there's a much more intelligent way, there's a much more efficient way to do these kinds of things, and that is to utilize what's called optimization. And the nice thing about optimization is that it's, for the most part, once you set up an optimization, it's not something that you have to be there to, to babysit it or to input things. It's a fully automated process, okay? So optimization essentially automates this process of choosing the values of these design variables or these parameters, and choosing the best possible values for them for your design. So you can see, it's a very powerful tool, and it's and it's one that's utilized in a lot of different settings to get commodities results. Okay. And it's especially useful in situations when you have multiple design variables that all kind of interact with each other in very complex ways, right? So if you look at the example that we have there, the signpost, probably you can design that signpost without optimization just because there's only one variable, right? But what if you have a situation where you have 3 design variables, maybe you have 4 design variables, 5, 6, 7, right? It becomes a lot more complicated because when you change one variable, it's going to change the performance of the other variables in kind of a non-linear way, right? And so for situations where you have multiple design variables, you kind of need to use optimization in order to choose their values in a in a very intelligent way. Okay. So that's kind of the objective, or that's kind of the goal of using optimization, is to kind of take this issue of choosing the values of these parameters and do so in kind of an automated, systematic way, that utilizes kind of our computer to the fullest. Okay. All right. Any questions in this? Okay. Okay, so let's go over a bit about how optimization works. And so, we're not going to get into the algorithms because that's kind of a whole nother class. People who took 454 with me last semester will tell you. But there is some prerequisite information that you need to know to at least set it up. So let's just go over some of the basics of optimization. Okay, so the interesting thing about optimization, so we kind of introduced it in this class as an engineering tool, but optimization actually doesn't even have its roots within engineering. It's actually an applied, it's actually an applied math thing, right? Okay. You could make the argument that engineering is just all applied math, and I wouldn't disagree with you, but specifically optimization started as kind of a math thing before the engineers started. And in fact, optimization really didn't have anything to do with anything physical at all. And so optimization has its roots in, if you have some function, right, any kind of function of any kind of variable, and optimization is basically the process in which you can find the absolute maximum of that function or the absolute minimum for that. So if you have some kind of function, so let's say we have a function of t, a horizontal axis t, vertical axis f of t, okay? So if you have a function that looks something like this, So optimization started as a way of, if you have just any kind of generic function, how do we locate, first of all, where the maximum is going to be and what the value of the function at the maximum is going to be. So the maximum of this function, you can see the highest value that the function attains is kind of at this peak right here. And the value of t, where the function attains this maxima, is right here. Okay. So oftentimes we call this t optimal. Right, so that's how it kind of started. So, basically mathematical algorithms are basically strategies or, ways to take a function and find its maxima, in a guaranteed kind of way. Okay. Now for a 1D function, it seems kind of silly. And so, for this function here, we found the maxima without having to do any kind of fancy algorithm. But again, when you have multiple variables, so let's say you have a function of 3 variables, 4 variables, 5 variables, at that point, it becomes impossible to plot it because you have just so many degrees of freedom. In those situations, you're going to need some kind of algorithm to find the maximum of that. As is the case with engineering designs as well. So when you have engineering designs that depend on multiple parameters at the same time, finding all of their optimal values at the same time is challenging without an optimization. Okay, so let's break this apart. So let's define some terminology here based on this kind of simple example that we have here. Right? Okay. Let's go over some terminology. Okay, so the first term that's important to understand with optimization is this idea of a design variable. Okay. So a design variable is some parameter of your system, of your engineering system, of your mathematical function that will influence the output or influence the performance of the system in some tangible way. In theory, for any given engineering design, there's probably dozens and dozens of parameters that go into the system, whether they be physical dimensions, choice of material, that also counts as a parameter. So whatever you choose for the material, but usually only a small subset of those actually goes to affect your performance in any given way. Okay, so for example, in activity 3, right? One way that you could have influenced the equivalent stress in the post is to change, maybe the physical dimensions of the sign part, right? So maybe you made it a little bit bigger. And while yes, that does change the weight of the signpost, and that does change the stress, probably it's not as significant as changing the diameter of the post itself in terms of increasing the safety factor, increasing the stability of the signpost. So whenever you have an engineering design, it's always a useful exercise to think about, what are the parameters of my design that are going to influence my result in the most kind of significant or tangible way. Those are your design variables. Okay? Now, if you, if you look at kind of the mathematical literature behind optimization, oftentimes the design variables are often called inputs to your system. But in an engineering context, we're often talking about engineering designs. I like to call them design variables. Okay. Okay. Second term that's important to know is what's called the objective function. So the objective function is, is a mathematical way or mathematical function for us to quantify the performance of a given engineering design. So basically, we have to have a way to, to basically, definitively state or systematically state whether one design is more superior than another. Okay. And the way that we do that is by computing the objective function. Okay, so let's do an example here just to kind of illustrate these concepts to you. Okay, so let's once again kind of look at our signpost activity from activity 3. Okay, so our signpost here, let me go ahead and draw it again. A little bit of a better drawing of the signpost, although it's a little bit wonky in this case. Okay. So part of activity 3 is that I tasked you with choosing an optimal value or choosing or modifying the signpost so that the equivalent stress in the post, falls below a certain factor of safety. So essentially that was our design problem that we were looking to solve in activity 3. Okay. Okay. So right away, we can see that we have our design variable here. Okay. So the variable or the aspect of our design or the parameter of our design that we can change, that we can tweak to affect its performance is the diameter of the post. So our diameter here, that's going to be our design variable. It's just one in this case, but we can have more design variables, of course. Right. Now, what do we choose for our objective function here? So, our criteria for a successful design is that our stress in the equivalent stress in our post falls below a certain threshold for safety. Okay. And so that's basically how we're going to quantify whether or how good our design is going to be, right? So basically, we want to say that better designs are going to have a smaller amount of stress compared to other designs. And so if we're comparing two designs kind of head to head, right? The design that has a lower equivalent stress in the post compared to the other one, that's going to be the more superior design. Our objective function basically needs to reflect this. Okay. Okay. So one way that we can design our objective function is to incorporate that equivalent stress directly into our objective. So if equivalent stress is the criteria that we're going to use to basically quantify or rate our designs as better or worse, then that factor should be in our objective function. Okay. Okay, so our objective function, so let me give it the very distinct symbol F. I know we use F for a lot of things in engineering. Okay, so our objective function here, in this case, it's going to be a function of the post diameter. Okay. This is going to be equal to minus the equivalent stress. Let me just give it a symbol. So minus sigma von Mises. Where sigma von Mises here, this is our equivalent stress. What we can basically say is that the performance of our design is inversely proportional to the equivalent stress of the structure. Okay. So basically, the higher the equivalent stress, the more negative this function is going to be. That means the worse design it's going to be. So if we want to maximize the performance or maximize the objective function of our design, we want to minimize the equivalent stress. Okay. Now, this is not the only definition for the objective function that works. So you know the definition of the objective function is usually something that you can change and modify. Right. So another way to get kind of a very similar result is if we define our objective function to be 1 divided by the equivalent stress. Okay. So that would kind of also give the same result. So if you have kind of a lower, equivalent stress, that's going to lead to a higher value of the objective function. So you want to maximize that as much as possible. Okay. So the objective function for any given problem is not unique. In fact, modifying it and tweaking it in certain ways will give you certain results better than others. Okay, so that's the idea. And so for any given optimization problem or any given design problem, you first need to identify what your design variables are going to be. So what are the aspects of your design that you can actually change to affect the results? And then the second thing you need to think about is, how am I going to quantify the performance of my design? So what factors or what quantities are going to go into my objective? All right, any questions on this? Okay, good. All right. So that's kind of just a very basic example of how take kind of a design problem and kind of put it in terms of the optimization terminology. Okay, let's talk about the the objective function a bit more, because that definitely warrants some more further discussion. Okay. So Mike mentioned above, the objective function is your way to basically quantify, what constitutes a good design versus a bad design. Right? So when you're forming your objective function, you need to think about, what are the most important aspects of my design that's going to kind of make it into the objective function. Now, for a finite element based engineering design, most of the time your objective function is going to consist of certain aspects of your FEA simulation results. So, in the last example that we talked about, the equivalent stress that we computed from the FEA simulation, that was the only aspect of the objective function. Okay. And that's really kind of the power of kind of merging together optimization with FEA, is that you can directly kind of take those simulation results and use that as a way to kind of modify or kind of optimize your design. Okay. So some examples of this would be things like equivalent stress. Some things like the deformation. Right, so those are kind of the basic things. So oftentimes, for most engineering designs, you want to minimize the equivalent stress, you want to minimize the deformation, because you want to make sure your part is going to be durable and safe. Okay. You can also think of quantities like the factor of safety. And other things as well. But if you're going to be using optimization within ANSYS, the FEA results in some way, shape, or form should be part of your objective function. Otherwise, there's kind of no point in using ANSYS to do something like this. Okay. Okay. But usually, the FEA results are not the only aspect that can make it into your objective function. There's often other constraints or often other issues that you need to consider as part of your engineering design. Because if you base your optimization just based purely on the equivalent stress, you can come up with a design that can minimize the equivalent stress. I think that's I'm pretty confident that you can do that in any given situation. But oftentimes, you're going to end up with a geometry that's either way too big, way too bulky. That's going to be either impossible to manufacture or way too expensive to manufacture. Okay. So oftentimes, other things that you may consider would be, maybe the total weight of the design. Right. So if you're doing any kind of application with aerospace, the weight of the payload or the weight of your craft is going to be very important. And so you need to balance kind of the weight together with kind of some of the other simulation results. Okay. Another very common one is the cost that's needed to manufacture. And so on the one hand, this could be just the total volume that your part takes up. And so that's just directly material cost. And so, a part that takes up, 1 cubic meter is going to be more expensive to manufacture than something that takes, 0.1 cubic meters. Okay. It's just a material cost. But also it could also be, the cost it takes to manufacture a certain type of geometry. And so there's a certain aspect of your geometry that's going to be more difficult or require another process to produce. That's something that you need to factor into your objective function as well. Okay. Maybe that additional process will lead to a better stress behavior. But you have to kind of weigh the pros and cons of whether that cost is going to be worth it for that, for the benefit that you get. Okay. Okay. So all of these factors that that you guys probably know already, and so you guys are all grad students in engineering, so you know that all of these factors are important considering engineering design. And so when you make your objective function, it's more about how do you take all these different kind of complex objectives, complex kind of ideas, and put it into a mathematical form that the algorithm can understand. And don't be afraid to do multiple objectives as well. In fact, most optimizations you're going to have multiple objectives. And so, I know in the previous example we just looked at one aspect, we just looked at just the equivalent stress, but oftentimes, you're going to have more than one aspect to consider. And that's kind of what makes optimization interesting, that you can consider multiple different perspectives or multiple different objectives and try to balance all of them together into one kind of design. Okay. So for example, so for the activity that we're going to do on Thursday, we're going to base our optimization primarily on 2 objectives. Okay. And so one objective that we're going to have is that we want to minimize. We want to minimize the total deformation of the part. Okay. Right, so we want our part to be sufficiently kind of strong and sufficiently kind of safe, and so we want to minimize that deformation. But at the same time, this part that we're gonna be doing is eventually going to be manufactured. And so we have to minimize the cost of production as well. So that means minimizing the weight, minimizing the material cost. And well, that's most of what we're gonna consider on Thursday, just minimizing the material cost. And what's interesting is that, these two aspects or these two kind of objectives are actually kind of at odds with each other. And so, what you're gonna see on Thursday is that, to minimize the total deformation, what you're gonna want to do, or what the program is gonna want to do, is that it wants to add more material. Because by adding more material, more mass, that increases the total stiffness of the part. That's gonna minimize the deformation, okay? But when you add more material, that also increases the cost as well. So these two are actually almost directly competing factors with each other. And so it's going to be very interesting to see on Thursday kind of how ANSYS is going to navigate this and choose an optimal design. And that's a case you're going to run into a lot, when you are, when you're doing these optimization problems. All right, any questions on this so far? Okay, all right, so let's talk about kind of one last aspect of optimization that is really important, which are constraints. Okay, now, I know we've used the term constraints for, for boundary conditions here in the class. But these are kind of different kinds of constraints. So these are not constraints on your physical FEA simulation, but these are constraints on the optimization procedure itself. And so just to kind of be clear, I'm going to call these optimization constraints. Okay. Now constraints, one way that you can think of an optimization is that, when you choose your objective function, right? How you choose to formulate your objective function is going to influence, the optimal parameters of, or the optimal values of your design variables, right? So depending on how you formulate the objective function, the values of the design variables are going to take on different values. Because remember, the objective function basically tells us, how we value or how we kind of quantify different aspects of the results of our finite element simulation. Okay, so for example, right, we go back to kind of the previous example where we're considering the deformation and the cost of our part. Okay. So one way that we can form our objective function is, let's say that we want to place more weight on our cost, right? So our objective function 3 times cost plus deformation. And let's say that we want to minimize this, and so. Right, and so in this situation, because we have the coefficient of 3 in front of the cost. That's gonna influence our design variables much more than the deformation. And so maybe, we're gonna opt for a design that's much leaner, so it has, it's much smaller physical dimensions than before. And of course, it goes the other way as well. And so if you instead put a coefficient of, let's say 5 in front of the deformation, then our design is gonna opt for, maybe a thicker, more material, more mass kind of design. Okay. So how we choose our objective function is going to influence our design variables. And depending on, which aspects of your design or which aspects of the outputs are more important, you can reflect that in the objective function. Okay. And so oftentimes, when you do optimization, it's very much an iterative process. So, oftentimes, you'll run an optimization, you'll look at the results, you'll think, oh, maybe that's not quite what I'm looking for, maybe I want to minimize the cost a bit more. Then you can kind of play around with the weightings to kind of, change that result. Okay. But this relationship between the objective function and the design variables, I would say is a bit more of an indirect relationship, okay? Oftentimes, when you have an engineering design or an engineering design problem, there are hard constraints or kind of hard kind of limits to what you can do with the design that you can't kind of, violate kind of no matter what. Right, so I think kind of the most obvious example of this is, making sure that your design fits within a certain kind of space, a certain kind of vault. Okay, because the way optimization works, and you'll see this kind of more closely on Thursday, is that optimization will take each of your design variables and kind of, almost kind of randomize it in a certain way, or kind of choose their values kind of somewhat randomly, and run a simulation and see how the results kind of turn out. And so if there are hard restrictions or kind of hard, constraints that you want to impose on your engineering design, you need to actually explicitly kind of define that, within the algorithm itself. Okay. So let's look at the example that we're kind of continuing on with this class. Okay, so if our objective function is kind of defined as it is above here, right? Where we have a 3 times weighting on cost, right? We may come up with a design that kind of optimizes the cost 3 times more than the deformation, okay? So let's say that the optimizer has chosen a design that minimizes the cost of production, okay? It also tried to minimize the deformation, but it didn't concern itself with it too much because the cost was kind of the main driver, was kind of the main output that we were trying to optimize. Okay, so we ran the optimization, on our design. Let's say we had 3 design variables, and we found one which minimized the cost as much as possible. Okay, so let's say that we took those parameters and we run a simulation with those optimal parameters. Right? So just to kind of see, so just to kind of look at our design and see how it's performing, right? And what we see from the simulation results is that the equivalent stress exceeds the yield strength of the material. Okay? Just bad, right? So if you have a design and you load the design in kind of a very typical way and you have your equivalent stress exceed the yield strength, then your part is just simply gonna break, it's simply gonna fail. Okay. And so even though this design, we were successful in minimizing the cost, obviously this design is invalid because the equivalent stress is too high. Okay. Now, we need to kind of go back and modify our design so that the equivalent stress meets this criteria. Okay. Now, one way that we can do it is that we can take the equivalent stress and include it in our objective function. Right, so that's one way that we kind of modify our process in order to account for that, but that doesn't, it doesn't solve our problem, for good, right? Because even though we can add the equivalent stress in there, but because we're emphasizing the cost so highly, even if the equivalent stress were put into our objective function, there's no guarantee that our result will actually, will still be below the yield strength. So when you include a certain output or when you include a certain aspect in your objective function, yes, the optimizer will try its best to minimize it. But when you start to include lots of different objectives, it just becomes one of many objectives. Okay. In this particular case where we have kind of a hard restriction, right? So, we can't have our design, have a stress that exceeds the yield strength. I would say this is more appropriate to include as a constraint. So people often get constraints and the objective function kind of mixed up because sometimes, they can kind of do the same thing. But the difference between, an aspect that you put in the objective function versus an aspect that you put it in a constraint is forced to be, satisfied. It's forced to be kind of followed. Kind of like how a constraint is in your finite element simulation. So, that's something that has to be done, okay? So for a situation like this, where you have, where it's necessary for a valid design to have an equivalent stress that's less than the yield strength, I would incorporate this as a constraint versus part of the objective. So that's essentially what a constraint does. And so a constraint is kind of a mathematical way to kind of force your optimization algorithm to get certain parts of your results, okay? And so, this is kind of one example. So I think this is actually what we're gonna do on Thursday, where we're gonna basically force our design to make sure that our equivalent stress is less than the yield strength, okay? But there's other things that you often want to constrain as well. So oftentimes, you want to constrain maybe the admissible parameter values, okay? For the different design variables, and so you don't want it to go below a certain threshold or above a certain threshold. Or maybe there's some aspects of the cost where you don't want the cost to exceed a certain amount as well. Okay? So when you have these kind of hard restrictions, and so things that you can't cross the line for your engineering design, you need to enforce those as constraints. So kind of the definition is constraints are conditions And so that's another thing that you need to think about when you're setting up your optimization is, what are the requirements? And so what are things that are required to happen in our engineering design? And what are things that we want to kind of, where it's not necessarily a requirement, but we want to kind of minimize or maximize as much as possible, right? So what factors that you put in the objective function and what factors you put in the constraints, is an important part of the optimization. Okay. You can think of constraints, I always like to think of constraints as kind of, as kind of like the laws that have to be followed. But oftentimes, there are certain, you're in certain organizations or situations where the rules are encouraged to be followed as opposed to being required to follow. So, so the things that are encouraged, you can think of those as being part of your objective function, and the rules that you have to follow, those are parts of your constraints. All right, any questions on this? Yes.
So on the scenario, if we choose like a equivalent stress to be under the yield strength, that's going to be basically just below the yield strength.
Exactly.
So we're basically choosing a factor of safety.
Exactly. Yeah. So you're enforcing basically a factor of safety in that situation. And that's important because maybe there's a minimum requirement for this design to have that factor of safety, and so you want to include that in the constraints so that you don't kind of leave it up to chance of the objective.
You decide that cost is 3 times more.
Yeah, I just did that as an example, but those weights and how different how you weight certain aspects of your objective function, that kind of depends on the objectives of the design. So I chose 3 just because 3 was the first number that popped into my head. But you're free to kind of choose that based on a situation by situation basis. Depends on your manager. That's probably the more important, the real answer to that question. Okay, so last thing I want to talk about today is kind of just an overview of how optimization actually works. And so, we've kind of gone over the terminology in terms of, how, what the different things you have to set up, but we haven't really talked about, how the optimization chooses, how it actually, works in general. So let's go over that. So granted, the computer is going to be mostly handling this optimization process for you. But it's still a good way, it's still good to understand what the computer's doing, so that you're not just wondering what the computer's thinking about for a good 20 minutes sometimes. Okay. So remember, the goal of an optimization is to kind of choose the best values of the design variables to, either maximize the performance of your design or minimize kind of the bad aspects of your design. That's kind of the definition that we kind of started with today. So optimization, we're choosing the best values of the design variables. We want to maximize the objectives, but we also want to satisfy the constraints. That was kind of the new thing that we kind of talked about just now. Okay. Okay, so how is the computer going to do this? Well, the best way to kind of see, right? The best way to kind of see how your design objectives, how the constraints are affected by the design variables is to change the variables and try. So in some sense, it doesn't really do anything too fancy. It kind of does what a human would do, where you would kind of change the design variables, kind of see what happens, and then and then choose where to go from there. Okay. So there's kind of a flow chart. I think the flow chart is kind of nice to look at for this. Okay. So let's say that you're starting out with some kind of initial design. So let's say that you have a CAD model for your design and you kind of initially kind of created it, okay? And from your initial design, you're going to run a simulation to test the design. So just based on the initial values of your design variables, you can run a simulation and see how how it performs, okay? Now, the next thing you want to do, okay, after you run your simulation is you want to make sure that all of the constraints are satisfied. You'll be surprised, sometimes, sometimes even in your initial design, your constraints may not be satisfied. You may have designed kind of a part that's gonna break from the get-go, okay? If the constraints are not satisfied, say that, we have a no. So let's say that your initial design is poor and that your constraints are not satisfied. What you're gonna wanna do is you're gonna wanna change the values of the design variables. Right, so you're gonna modify the values of the design variables, and then run the simulation again, and then check to make sure that your constraints are satisfied, okay? Okay, well, let's say your constraints are satisfied. Say our constraints are satisfied, yes. And so from here, what you're gonna do is you're going to evaluate your objective function. All right, and then once you've evaluated your objective function, you'll have a number or an evaluation in terms of, how good your design is, okay? Okay, and so from here, generally what you're gonna wanna do is you're gonna once again try to modify your design variables. But this time you're gonna do so with the objective of improving your design. Right, because we know that, our objective function or our optimization objectives, they are all gonna depend on the values of the design variables, okay? And so, if we do get a simulation result that does satisfy our constraints, right? We're gonna wanna try to improve that as much as possible. And every time you change the design variables, you're gonna need to run the simulation again, in order to get the results, okay? And so you can see here, we kind of have a cyclic kind of pattern to this thing. So, every time you run a simulation, you're gonna check to see if the constraints are satisfied. If they're not, then you change the design variables to satisfy the constraints. If they do satisfy the constraints, you evaluate the objective function, you modify the design variables, and all of this kind of goes into kind of a loop, okay? And so everything in this box right here, this is essentially what's happening during an optimization algorithm or optimization process. So during an optimization process or optimization algorithm, the software is going to be running multiple simulations, and each time it runs the simulations, it's going to slightly tweak the values of the design variables, okay? And so you're going to see that on Thursday. So on Thursday, you're going to see that our optimization is going to be kind of choosing different design variables, running a simulation, seeing how things go. If things improve, that's great. If they don't, then then you just kind of modify and kind of go on to the next one. And all throughout this process, the software is keeping track. And so it's kind of building this kind of table of all the different design variables and how they performed in the simulation. So every time you run a simulation, it's going to remember, whether it satisfies the constraints or not, what the value of the objective function is going to be, okay? And when the algorithm is done, it's going to choose the best combination of design variables that first of all satisfy the constraints, and second of all led to the best value of the objective function. So in a nutshell, that's how optimization works. And so it's going to be making changes to your design variables, running the simulation, seeing how the results pan out, and kind of doing this over and over and over again. And then, by the law of large numbers and the law of averages, eventually you're going to come up, you run enough simulations and you're going to reach a point where your result is going to be optimal, for that set of design variables. Okay. Now it's not a random process, I think the biggest mystery boxes are, the ones that I've circled. So how the algorithm chooses to modify your design variables, how it chooses the next values. There is a lot of math to that, and so anyone that took 454 last semester will tell you there's a lot of complications with that step. But we're not going to go over that in this class because there's just not enough time. Essentially that's kind of how these optimization algorithms work. And kind of what you're going to observe kind of from, at least from the outside perspective on others. All right, any final questions before we wrap it up? Yes, sorry.
How does it know when to stop?
Yeah, so there's a lot of different criteria that you can use to stop. And so one way, or probably the most common way, is that you can tell it a maximum number of simulations to do. So it said that, don't do more than 100 simulations. And so it'll find just the best value out of those 100 that you choose. Another way that it stops is that, maybe it finds a location, or maybe it finds a combination of design variables that is really optimal. And no matter how it chooses to change, it doesn't find anything better. And so if it finds a spot that's really good, and let's say that it tries 10 other simulations within that vicinity, that none of them lead to an improvement, then that's another indication that the optimization algorithm has converged, and then it can stop. But most commonly, it's you're going to hit that maximum simulation limit, just because these problems are often too complex to kind of fit that criteria. Any other questions? Okay, all right. So that's all we got time for today. And so when we come back on Thursday, we'll be doing our ANSYS activity 6. So look forward to that. And then I'm hoping to finish all your midterm project ratings by end of the week. So thank you guys for coming today. Hope you guys have a good rest of your day. I will see you guys on Thursday.
Professor?
Yeah.
I have a question about the assignment for this week or before spring break.
Yeah.
I know problem 6 was optional, I think it was changing the material. I just wanted to check, is the mesh convergence test also optional, or is that required?
That was also optional as well.
Okay.
Yeah, that's going to take way too long. Even with the original material, even just getting one simulation to run with one mesh is not trivial. And so yeah, the mesh conversion test also optional.
Okay, cool. Just making sure. Thank you.
Right, but that's all and there, nice. Maybe the back and forth. Like analysis.